So good evening, everybody. So we have completed the non-uniform flow one part, which is gradually varied flow. So in the gradually varied flow, I have taken you slowly towards the gradually varied flow equation. Then gradually varied flow equation applicable to wide rectangular channels. Then I have taken classification of channel bottom slopes. Then I explained what is backwater curve, what is drawdown curve. Then I have taken to you what are the water surface profiles, what is mean by M curves, S curves, C curves, H curves, A curves. Then I have taken to you how to calculate the length of the water surface profile. So these are the various topics that I have dealt and then followed by problems. So that we have completed one part. Now the last part of non-uniform flow is rapidly varied flow, which is exactly opposite to gradually varied flow. If you remember in gradually varied flow, I mentioned that the depth variations are very small over a long distance of channel. If you cover a long distance of river, the depth variations over this long distance are very small. There is some variation of depth. Because of the variation of depth, only we call it as non-uniform flow. If there is no variation of depth, we should have called it as uniform flow. But why we called it as non-uniform flow? Because there is variation in depth of flow. But that variation in depth of flow is very small over a long distance of the channel. That is why it's called as gradually varied flow. But if suppose the depth variations are very large in a short distance of canal, the depth variations are very, very large in a small distance of the channel, then we call it as rapidly varied flow. The depth variations are very large in a small distance of channel. Then we call it as rapidly varied flow. The best example for it is the flow at the foot of the spillway. The water which flows over the spillway at the bottom, at the foot of the spillway, then actually the rapidly varied flow comes into picture. And that rapidly varied flow results in formation of hydraulic jump. The rapidly varied flow results in what finally? Hydraulic jump. Hydraulic jump results in what? Energy dissipation, energy loss. So this is the topic that which we are supposed to now take up. So now you understand first what is rapidly varied flow, what are the examples of rapidly varied flow, and for mind we should fix rapidly varied flow means it results in formation of hydraulic jump. We create the conditions of rapidly varied flow at a particular point at the foot of the spillway. Or suppose when the steep slope suddenly it makes flat, at that point definitely the flow is rapidly varied flow and hydraulic jump forms. So these are the some of the examples. And now we need to analyze whatever the hydraulic jump forms. What are its characteristics? How to understand more about the hydraulic jump? And finally, we need to calculate what is the energy loss in case of a hydraulic jump. So these are the various topics. So the first today's thing is definition of a hydraulic jump, definition of rapidly varied flow, and general equation of hydraulic jump. Like general equation of gradually varied flow, general equation of hydraulic jump that we will take in this lecture. Then continuation lecture is what is the equation for a rectangular channel, because we don't do other channels actually. Like gradually varied flow also, I did general equation first, then applicable to rectangular channel. Here also, if this lecture is devoted to general equation, the next lecture is devoted to rectangular channel. What the next third lecture is going to be? Energy dissipation, energy losses. Once energy losses are obtained, what are the applications of hydraulic jump? That we will take it up. That ends the third. So once these three lectures are over, the fourth lecture is problems. So total lectures in this particular rapidly varied flow are four lectures. Lecture one is rapidly varied flow, hydraulic jump, and general equation of hydraulic jump. Lecture two is the equation of hydraulic jump in case of rectangular channels. Equation three is energy loss and length of the jump, and basically applications of hydraulic jump. With that, the theory part is closed. The last part is we will take it up the problems, four lectures. So let us go into the first lecture, right? So topic is rapidly varied flow. What is rapidly varied flow? That is first thing, right? The rapidly varied flow is a part of what? It is a part of non-uniform flow. If the change in depth of flow, if the change in depth of flow is large, this is very, very important word. In a relatively short distance of the channel, the flow is called rapidly varied. Example, flow downstream of a spillway. Flow in a canal below a sluice gate. These are the two things. Suppose if I draw a spillway for your understanding sake. Suppose this is the spillway. Now, if the flow which takes place here, this is how it takes place, right? The depth is y1, this depth is y2, right? These are all rollers. So if I take it from here, basically to this place, this is rapidly varied. So this is what the rapidly varied flow. This part is spillway. Where it occurs, the foot of the spillway. This is the foot of the spillway. So this is what, this is water surface, right? Then now next definition is, what is hydraulic jump? Rapidly varied flow is always associated with a hydraulic jump. Always. The hydraulic jump is defined as the hydraulic jump is defined as sudden, please remember, sudden and turbulent. Turbulent, TURBU, passage of water from a supercritical state to a subcritical state. Please, once again. So it's a sudden and turbulent passage of water from a supercritical state to a subcritical state. It is what we call it as hydraulic jump. When flow, rather than that I can read, when a supercritical flow meets subcritical flow, hydraulic jump forms. This is the next thing. What is actually the hydraulic jump? The formation of hydraulic jump is always associated with formation of turbulent rollers, resulting in dissipation of energy. This is first thing. So still I can make it. Hydraulic jump forms. All are same sentences. I am writing in different ways to make you to understand. Hydraulic jump will form when water moving at same sentence, that nothing difference. When water moving at supercritical velocity in a relatively small depth strikes water moving at supercritical subcritical velocity. In a relatively large depth. This is what is the case. Same above I dealt with. It occurs at the foot of the spillway right? Then flow in a canal below a regulating device when steep slope suddenly changes to flat slope. So these are the conditions under which the hydraulic jump forms. Already I mentioned when the hydraulic jump forms, what is the result of that? It is always basically loss of energy. Hydraulic jump results in hydraulic jump results in loss of energy, and this is initially unknown. This we have to find out. And to find out this, actually, the hydraulic jump can be analyzed using momentum equation. Using momentum equation. So this is the first thing. Next, what is the hydraulic jump equation? This is what I will take it up. So first thing is, before going to that, what are the assumptions? Number one, what are the assumptions actually? Before and after the jump, the flow in the canal is uniform and pressure distribution is hydrostatic. This is first assumption. So that means except the where the rapidly varied flow is formed, before that, after that, it is uniform flow. And pressure distribution is always hydrostatic. That is number two. Then length of the jump is small so that the losses due to friction on the channel floor are small and hence neglected. This is second. The friction losses are neglected. Number three. The channel floor is horizontal or so steep that the weight component of water comprising the jump is negligibly small. These are the three assumptions. Now, after this, I will go for the equation. Those assumptions are very simple assumptions. What are the simple assumptions we have taken? For example, at the location where the hydraulic jump is formed, it is rapidly variable. Before that and after that portion, naturally the flow is uniform. That is first assumption. Second assumption is the pressure distribution is hydrostatic. Third one is the length of the jump, length of the hydraulic jump, where it is mainly rapidly varied flow, is so small that the friction, because friction losses depends on the perimeter. Perimeter is means it depends on the length of the channel. So that length is so small that the frictional resistance or frictional forces can be neglected. Next, what are the things which we counted actually? There, number one is pressure. Pressure is hydrostatic. Number two, frictional losses neglected. Number three is the channel floor is hydrostatic, horizontal. That means anywhere you take the weight component is same. So the weight component in the direction of flow, any place you can take it as same. So that's why it is negligibly small in the direction of flow, because the total will be acting only in the vertical direction. That is what is the third actually. So after this assumption, now I straight away take you to the equation. So now before taking up the equation, consider a hydraulic jump formed, a hydraulic jump formed in a prismatic channel with horizontal floor carrying a discharge. You, this is first thing. Let the depth of flow before the jump is y1 and after the jump y2. This is next point. 2 points I mentioned. Right? Now I will draw the picture actually, how it looks like. For example, if I take this as the floor, right? How the hydraulic jump looks like. So this is here at this. This is the thing. So here, this is y1 before, and after it is y2. This is what we call it as rollers. So this is section 1 1, and this is section 2 2. This is, and the discharge flowing is Q, right? Now, if I take the pressure distribution at this place, naturally hydrostatic pressure distribution is triangular. Similarly, if you take the pressure distribution here, this is how the pressure distribution. This is the pressure distribution, right? If I take it, this is P1, this is P2, the pressure distribution, right? Next, from here to here, we call it as length of jump, right? Now, if I take the sections actually, at this place, if I take the section 1, suppose if you take it, this is how the channel is, right? Now, here the depth is here only small depth. So, this is y1 equivalent to it actually, right? This is water surface. So, this is all channel, right? Then, so this is section 1. And here at section 2, if I take it, so this is y2, right? If I take it y2, right? Okay. Now, if I take actually, suppose if I plot a curve taking x-axis as a f, I will tell what is f, and y-axis the depth of flow y I have taken. Then I got a curve like this. This is how I got a curve. At this curve, there is the F is nothing but this is called as specific force. What is that? I will explain. X is specific force. This is depth of flow. So I get at some point this minimum specific force. Corresponding to this minimum specific force, the depth is called critical depth. Beyond that, you take any specific force, there will be F1, F2. F1 is equal to F2 that you can see here. But there are two depths of flow you can see. This is Y1, this is Y2, right? This is what you should understand. So if I draw that actually, so this is what we call it as YC. Y2 is greater than YC and Y1 is less than YC. That's all what I want to tell to you at this point. So this is section 2. Now I will take you to the next point, then we will see. Now what I told, draw a graph such that take specific force specific force F on x-axis and depth of flow on y-axis, right? The observations are at minimum specific energy, minimum specific force, there will be only one depth of flow, which is called critical depth. Apart from that, apart from that, at any at any other at any other point for a given specific energy, there will be two depths of flow. These two depths of flow where specific force is same are called are called actually they are called actually y1 and y2 are called conjugate depths. That concludes this lecture actually. Thank you very much.
Like, share, and subscribe. Hit the bell icon for more updates.